Let us now talk about more operations on binary heap. Let's first discuss decrease key operation. We have a binary heap, we have index of an element which we want to decrease, and we have new value for this element. So index 3 belongs to this element 80. We want to change this value from 80 to 5. So after you change it to 5, what will happen? The min heap property will be violated, right? Because you will have a parent of it which has greater value than this node, right? So you need to correct this heap after updating the value, right? It's not only about going to that index and updating the value. We need to make sure after we update the value, we have the correct value. So this should be our modified min heap. Since the newly updated value is the smallest, it should go to the root, right? And then subtree should also be heap, right? They should also have the heap property. Let's see one more example. In this example also I've considered I equal to 3 and we have changed this to new value 10. Now once you change it to 10, the 10 should also become root, right? And left and right subtree should be modified. Suppose you were changing it to something like 30, then this 30 would not have become root. It should have gone something like someplace like here, right? So we need to make sure that min heap property is maintained once you update the value. Now please pause this video and write a function that takes a heap as input, an index as input, and a new value input, updates the heap and make sure after updating it is still a heap. Let us now talk about the idea of decrease key operation. So what we do is we go to that index and change that value. So I've changed this value to 5. After I change this value, I do something like insert. I compare this new value with the parent, and if parent is greater, I swap these two values, right? In this case, parent is greater, so we swap these two. So we have now 520. And we keep doing this thing while parent is greater or we have reached the root node. So again, we compare it with the parent and parent is greater, so we swap these two. So we have 5 now here. And now we have reached the root, there is no more parent, so we stop here and our tree is heap. Now please pause this video again and try to write a function that implements this logic. Here is implementation of decrease key operation. We are assuming that this function is written in the min heap class that we discussed. So this function has access to ARR, size and capacity. So what we do in this function, we have done similar to insert function. We are taking index of the element that we want to update, and we are taking a new value for this element. We simply go to that index, update the value, and after that, we simply go to the parent while parent is greater, right? So we are simply doing, if parent is greater than the current element, then swap these two elements and move to the parent, right? Keep doing it while you do not reach the root node or you do not reach a node which is smaller. Do not reach a parent which is smaller, right? Now what is the time complexity of the solution? We are simply going to traverse across the height, right? And the worst case, we will traverse the whole height. So the time complexity is big O of log n for decrease key operation. Let us now talk about binary heap delete operation. So we are given a min heap and we are given an index. We want to delete the element at this index. So in this min heap, we want to delete the element 40. After you delete 40, your min heap should change to this min heap. So when you're deleting an element, you need to ensure that your modified min heap follows these two properties. The first property is it still has every node smaller than all of its descendants. Second property is it should be a complete binary tree. All the levels should be completely filled except possibly the last level, and the last level should be filled from left to right. Let's see this example. Here we want to delete 12 element at index 3. After you delete 12, your heap should be modified to this heap, right? It is still a binary heap. It is a complete binary tree, and it is a min heap. Every element is smaller than all of its descendants. So please pause this video now and try to think of an approach that deletes a given element at a given index and make sure that the modified tree is still a binary heap. Let us now talk about algorithm for delete key. So the idea is simple. Your delete function mainly calls two functions. It first calls decrease key for the given index and the modified value is minus infinite. So when you call decrease key with minus infinite, this key reaches to the root. And once this modified minus infinite key reaches to the root, you simply call extract minimum. That's all. And you've deleted the key. Let's see this example. We wanted to delete this key. So what we did, we called decrease key with this index, the passed index, and the decreased value as minus infinite. So what do you do in decrease key? You replace it with minus infinite, and then you compare it with the parent, right? And if the parent is greater, then you swap it with the parent, then you again compare it with the parent, and after doing all these operations, you get this binary heap. This is what happens when you call decrease key on this particular heap with index as 3 and new value as minus infinite. Once you call decrease key, now you call extract minimum. And extract minimum we have discussed in the previous video. What are we going to do in extract minimum? We are simply going to swap it with the last value. So once you swap, what will happen? Minus infinite will come here and 45 will come here and size will reduce by 1. And after that you will call heapify for this 45. Once you call heapify, what will happen? These two will be swapped. So you will have 10 here and then you will have 45 here. And then these two will be swapped in the heapify operation because recursively heapify will be called for this. So you will have 20 here and then you will have 45 here. So that's how you get this modified binary heap once you call extract minimum. So we have mainly called decrease key and extract minimum. Now what is the time complexity of delete function? Please note that decrease key takes big O of log n time and extract minimum also takes big O of log n time. So overall time complexity for delete function is big O of log n. Let us now talk about build heap operation. So the build heap operation is we are given a random array. Elements might be arranged in any order and we want to convert this array into a min heap. So let's see this array as an example. We have this array, elements are arranged in any order and this array represents this complete binary tree, right? Every array represents some complete binary tree, right? And this is the complete binary tree represented by this array. Now we want to convert this complete binary tree into a min heap like this, right? So our array should be modified according to nodes of this min heap, right? 2 should come first at index 0, then 4, then 8, then 5, then 10, then 20 and 30. You can notice that 2, 4, 8, 5, 10, 20, right? Let's see one more example. 30, 20, 10. We have 30, 0 index, 21 index and 10 at 2 index. We want to convert this array again into a min heap, right? So it can be either 10, 20, 30 or 10, 30, 20. We just want to make the random array into a min heap. Now please pause this video and try to think of a solution that takes the array as an input, rearranges the array elements so that array represents a min heap. Let us now talk about working of build heap function. What we do in build heap is we begin with the bottommost rightmost internal node, right? Let's say the index of this node is I. We call min heapify for this and then we call min heapify for I minus 1. Then we call min heapify for I minus 2, I minus 3, I minus 4 and so on until we reach 0, right? So then we at the end we call min heapify for 0 also. So that's all we do in build heap function. Let's see this example tree. What is the bottommost rightmost internal node? This one is the bottommost rightmost internal node. We called min heapify for this. We convert this into a min heap. Then we call min heapify for this. I minus 1, right? Then I minus 2, then I minus 3. So we keep calling min heapify in this order. First for this, then for this, then for this, then for this, and finally for this. And the assumption of min heapify function is when you call min heapify for an index I, its left and right should already be heapified. And that is the reason we are starting from bottom and we are going to the top direction. Because when you come to an upper level, your lower levels are already heapified. That's the idea. Let's see the working of this idea for this example. So what is the index of bottommost rightmost internal node? This is the bottommost rightmost internal node, right? And we begin from here. We call heapify for this part, right? So we call min heapify for index 2, right? When you call min heapify for this, 8 comes to the root of the subtree and 20 goes down. Now you call min heapify for this, right? So this converts into this tree. Now you call min heapify for 0 and your whole tree is heapified. And finally you have a binary heap. That's how build heap function works. Now, how do we get the index of bottommost, rightmost internal node? This is the expression that we are using for this index. And how do we get this index? See, the last node will be at index size minus 1 if size is the number of elements present in the heap. So for example, if there are 11 elements in this heap, then size is going to be 11. And index of last node is going to be size minus 1, right? And what is the index of the parent of the last node? Well, how do we get the parent? We do size minus 1 by 2, right? We mainly do I minus 1 by 2 to find out the parent. And bottommost, rightmost leaf internal node is going to be the parent of last leaf, right? That's the idea we are using. So we know the index of last node. We simply use the parent formula to get the required node. And we begin from here, right? And then we decrement it one by one. And we do decrement it while this is greater than or equal to 0. We stop at 0, the root node, and we simply call min heapify for every index. Let us now talk about time complexity of build heap function. If we take a look at this function, it looks like big O of n log n function, where n is the number of nodes in min heap. Because what we are doing, we are calling min heapify, which is a log n function with n for a min heap with n nodes, and we are calling it for n minus 2 by 2 to 0 in a loop, right? So it's clearly an upper bounded by n log n function. But if we do tight analysis and we do some mathematics, we can prove that this build heap function is a big O of n function. It takes linear time. And this proof is based on the formula that in a complete binary tree, number of nodes at height h is upper bounded by this. There can be at most these many nodes in a binary heap of height h, where n is the number of nodes in the heap, h is the height at which we are counting the nodes. So we consider these nodes as 0 height nodes, these nodes as 1 height nodes, 2 height nodes, and 3 height nodes. So how many nodes we have in this binary heap at height 0? We have 8 nodes. And how many total nodes we have? N is 15 here. Let's try to get these numbers here. So n is 15 here. And if we want to know the number of nodes for h equal to 0, we have n divided by 15 divided by 2 raised to the power 0 plus 1, which is 15 divided by 2, 7.5, so we get 8. Right, so we have 8 nodes. Now if you use the same formula for height equal to 1, you will be having 15 divided by 4, which is 4, right? Ceiling of which is 4. So you have 4 nodes. Even if you remove some nodes and apply the formula, you are going to see that this formula is true. That's the upper bound on the number of nodes at a height. So we use this expression to find the overall time complexity. What we do in build heap is we call heapify for all the levels starting with height 1, right? We start with height 1 nodes, right? In the worst case, right? Or you may skip some height 1 nodes also. That's why we have used big O notation in the expression. So we begin with height 1 nodes first, right? So this is height 1 nodes. We are actually going to begin this, but we are going to consider all the nodes of height 1 in the time complexity of this expression. We are finding an upper bound. So we run a loop. We call heapify, which takes big O of h time for any height, and we are calling this min heapify for these many nodes, where height goes from 1 to log n. Now I have taken these things inside and put big O outside. And I've taken this n outside. So my expression is that I want to analyze is 2 raised to the power h plus 1, h divided by 2 raised to the power h plus 1, and sum from h equal to 1 to log n. And I've removed the ceiling function because we have big O notation, so we can ignore 1s and 2s. Now the point is, sum of the series for infinite terms is 1, and I've shown this here. So that is how we are getting big O of n time complexity. Now how come sum of the series for infinite terms is 1? Let's write down the series. For h equal to 1 to infinite, say the sum of the series is s. So we can write the sum as 1 by 2 square, 2 by 3 cube, 2 by 2 cube, 3 by 2 4, 4 by 2 raised to the power 5. Now if I do s by 2, I get this modified series. And if I do s minus s by 2, I get this series, right? Which is geometric progression. Now my s by 2 is a geometric progression. I simply apply the formula of infinite series here. I get 1 by 2 square a upon 1 minus r, and I get this expression is 1 by 2. So sum is 1. Right? So I got the sum of the series as 1. I simply put this sum as 1 here. And this is sum of infinite series, and we have sum up to log n. So we have big O, so we can put up our values. So value of this expression is big O of n. So time complexity of build heap is big O of n.